Okay, this is sample problem 8.2. Arrange MgO, CaO, and SRO in order of increasing lattice energy. Okay? Lattice energy. So the idea here is that when we take an ion that has a positive charge and combine it with an ion that has a negative charge, remember the names, cation, that's positively charged, anion, that's negatively charged. There is an energy of attraction, and it's proportional to the amount of positive charge times the amount of negative charge divided by the distance between the ions. Now, that's for a simple two-body problem right there. But the lattice energy, which is the combination of all the attractive forces, all the attractive energies, sorry, that is going to follow the same pattern. So even though a ionic compound doesn't exist as two individual particles, the lattice energy essentially follows the same physics or similar physics as the attraction. So here's what happens. When we're talking about an ionic compound, the ions are actually right next to each other. There's really no distance between them. So what we do is we ask ourselves, how far is the distance between the centers? Okay? So how big, what's the size of this ion? And what's the size of this ion? That's an important factor, because the overall distance is the sum of those two radii. Okay? So let me go over these particular ions. The ions that we have here are magnesium, calcium, and strontium. Those are the cations. The anion is the same every time. Okay? So the oxide's not an issue here because it doesn't change between these three compounds. If there's a difference in lattice energy, changing the ion here can change the lattice energy. Now here's the pattern. As you go down the periodic table, the size of the ion gets larger. Okay? The strontium ion is larger than a calcium ion, which is larger than a magnesium ion. So if I wanted to show you it this way, I could write it this way. The magnesium ion might look like this, and then the oxide ion might look like this. The calcium ion would look bigger, and the oxide ion would be the same. And then the strontium would be even bigger than the calcium, and the oxide again would be the same, right? Oops, I'm not drawing the oxide the same. I'm trying to, okay? So what that means is this distance is going to be larger than it would be here, and larger than it would be here, okay? Because every time you get a bigger cation, the distance between the ions gets bigger. So what happens is, as this gets bigger, by the way, there should be a negative there. As this distance gets larger, okay, so if this goes up, if the distance goes up, the energy goes down, right? That's the idea. It's an inverse proportionality. If something in the denominator gets larger, the ratio gets smaller. So the lattice energy would get smaller. So every time the size of the cation gets larger, the energy should go down, the energy of attraction. So since strontium is the largest, its lattice energy would be the smallest. So I'm going to write it this way. SRO would have a smaller lattice energy than CaO. And that would have a smaller lattice energy than MgO. Okay? That's essentially the idea. So another way of thinking about it is it's getting bigger in this direction, or larger. Lattice energy, right? The energy of attraction between those ions.